All right. We talked about a lot of amplifiers, right? And we did kind of like a full analysis and developed a whole method to look at them. But let's look at something simple in terms of an amplifier. So let's say you have an amplifier, right? It can be a MOSFET or bipolar. Let's make it MOSFET for a change now. And then you have, let's say, some sort of a resistor R2. So if I ask you what is the gain, and let's think about that this is being driven by an actual voltage source. So there's no source resistance, an ideal voltage source. And all that I worry about is that I have a relatively large capacitor in the load, as a load. Now, this is a kind of a simplified example to demonstrate a point. What is the gain of this stage? What is the DC gain, or like the AC gain of the signal, this thing? I'm not showing the biasing details, right? There has to be some biasing thing here. But I'm not showing it. Or I am showing it now, I guess. But so what is the gain? Let's say that's the only capacitor, and forget about that. But the basic gain of this thing is negative GM R2, right? So this is the gain of this thing. And then what is the bandwidth? What is the omega H of this thing? Well, the omega H of this thing, if you have a single capacitor, is going to be exactly 1 over that time constant. It's going to be 1 over R2 CL. Right? Now, interestingly, if you look at the product of these two, what do you get? The R2 cancels. Well, of course, I'm looking at the magnitude of gain. So it's going to be GM over CL. So you see a lot of these performance limits of this nature, a lot of times kind of boil down to some sort of a GM over some capacitor, which kind of makes sense from a physical intuition, right? What determines the speed of something? The drive power. Let's say I want to move this thing. If I want to move it fast, what are the two things that matter? How much force I apply. If I can apply a lot more force, I can move it faster. And how heavy this thing is. The force is the drive, is the GM. The weight is the capacitor, right? The mass is the capacitor, right? If you think about it. So the more drive I have and the lighter the thing is that I'm trying to move, the faster I can move it. But you can see that this is actually independent of the gain itself. So what this means is that if I pick a large resistor, try to get a lot of gain, right? So this is log of omega, and then this is 10 log of the magnitude h of j omega. Right? Or 20 log of h of j omega. Then what you see is that if I pick a large r, I will get a large value here, but my omega h is going to be small. So I'm going to drop faster. Drop earlier, not faster, drop earlier. Now, if I reduce my resistor, right, my omega h will go up. But my gain is lower. So, and as I lower r, well, this is not a straight line, but as I lower r, so this is r going down, you see that my gain goes down, but my 3 dB bandwidth is increasing proportionally. So there appears to be, and there is some sort of a trade-off between the gain and the bandwidth of a system. In fact, if you look at this gain bandwidth product, where is that on this plot? This, we call it actually, oh, well, we'll see what we call it in a second. Do you agree that if this was 0 dB, meaning a gain of 1, this point is this product? Because that's where basically the gain is 1. And we call it omega unity gain bandwidth. Or unity gain frequency, omega u. So there appears to be the gain bandwidth product, at least in this simple example, to be fixed. Now, if you write more elaborate examples, you will see that it's not exactly fixed, but it's kind of like changing more or less, not a lot, if you calculate this product. And we'll see that there are actually different ways of achieving this, lowering this thing. So what you're doing is, as you're lowering R, you're throwing away the gain here, and you're recovering it here, right? So there's this kind of like notion of gain bandwidth product being a constant in general. Now, this is not exactly, so let me tell you what the general conception is. The general concept, there are people who say, oh, the gain bandwidth product is a constant, or more or less is constant, right? Not exactly. The real trade-off, as we will see later on, and I'm going to just give you a little bit of preview, is between the gain bandwidth product itself and the delay, or the latency of the system. And this happens in a lot of different systems. It actually even happens in mechanical systems. 2, if you want something, a large gain bandwidth product, you can achieve it by allowing for a larger delay. For example, turbochargers in cars. If you think about it, there's this thing called turbo lag. You want a lot of power, you can actually get it, but it will be delayed. I mean, if you want to get a lot of power in mechanical internal combustion engine, you will have to wait for it. So there is this it's actually a much more fundamental trade-off, and we'll talk about it several times in different contexts as we go. But this is kind of like the first introduction to it. But this gain bandwidth product within one stage is something that you can actually treat as within a single stage in a single system like this. Then yes, there is some sort of a trade-off. Now let's assume that. Let's start with the assumption and see where it leads us in terms of what we can do in terms of the overall system. And you will see that actually the statement that we made earlier is relevant and how it applies. So imagine we are trying to make an amplifier. So let's put this away for a second. Imagine you're trying to make an amplifier of a certain gain. Let's say I want to make an amplifier with a gain of 100. Total amplifier. We are trying to design an amplifier with a gain of 100. As a simple example. Actually, let me bring this back because I have some space there. So if I wanted to make an amplifier, so this is an amplifier with a gain of 100. AV equals 100. Voltage gain of 100. And let's say your gain bandwidth product for the devices that you have and the capacitors that you have is something. So let's say this gives you a bandwidth of, I don't know, just pick a number. Let's say it gave you a bandwidth of 100 megahertz, right? Let's say the response of the system was a first order system. So this was a first order system. In other words, it's 1 over S over omega 1, the transfer function of this thing, or not F, it's A0, the gain of that thing. And let's say it follows this kind of gain bandwidth product trade-off. So let's say it's made out of these amplifiers that we talked about. What if I could make instead of a gain of 100, if I make a gain of a 10, so if I make an amplifier with a gain of 10, what do you expect its bandwidth to be based on this calculation? A gigahertz, right? If the gain bandwidth product was constant, then I get a gigahertz from a gain of 10. Now, what if I take 2 of these? So this is a 1 gigahertz and 1 gigahertz bandwidth with a gain of 10. What is my overall gain? What is my overall gain? 100. So I have the same overall gain. What is my overall bandwidth? Well, we can calculate it, right? Because the new transfer function is basically A1 or whatever, okay, right? Squared, which is A0, A1 being 10, divided by 1 plus S over omega, well, we call this omega 1. Let's call this 1, A1, and make these 2's. A2, omega 2, squared. Because I have the transfer function multiplied by itself, right? Because it goes through itself twice. So each one of them has a transfer function of A2, has a first order transfer function of S over omega 2. And you have them cascaded, so they get multiplied, the two transfer functions, right? So what is the bandwidth now? Well, I have to calculate the magnitude square of this thing and set it to 1/2 and find the frequency, right? What we do is that we basically want to say 1 over 1 plus j omega over omega 2 squared, magnitude squared. So we want to calculate the magnitude of this thing. Or if the magnitude of this thing has to be 1 over square root of 2 at the frequency of interest. So this is omega h of this compounded system. So I need to solve this. So magnitude square of this thing is actually simple because it's going to be 1 plus omega h over omega 2, each one of them squared, is equal to 1 over square root of 2, right? So then it becomes omega h over omega 2 is square root of 2 minus 1, right? Square root of 2 minus 1 is whatever it is, square root of 2 minus 1 is syntax error. Is 0.64. So this is 0.64. But omega 2 was what? I mean, omega 2 was 2 pi times 1 gigahertz, right? So it means that the new cutoff frequency associated for this compounded system, this whole thing, has a bandwidth of 640 megahertz as opposed to 100 megahertz. And it has the same gain. So we got a significant improvement by breaking the gain into 2 stages. And remember when we were doing that design example a few lectures back, he said one of the pathways is that instead of having a large resistor is to have multiple stages and breaking that resistor because that was the time constant that was dominating. Now, do you think this is the best we can do with this? Or no? You can see this from this example. This was a significant improvement, right? What we did, instead of getting 100 in one stage, we got 2 stages of 10, and we got a lot of gain. Is there a catch? Well, there is one catch. You could say, okay, the power consumption of this thing could be twice as much, fine, and then you will do a problem set where you do a power constraint, and you see you can still gain a lot. So let's say power is not, so yeah, you're burning more power because you have 2 stages instead of 1. But any other catches? Anything else? Yes?
The delay is doubled.
The delay is doubled, right? Good observation, right? It goes back to the conversation we had. So that's how we got around that trade-off, really. It's because it seems that our gain bandwidth product has significantly improved, right? Because the gain is the same, but the bandwidth is like 6 times larger, more than 6 times larger. So that's why we are doing that, playing with that trade-off. We are trading delay with that. There's another thing, is that if this amplifier is to be used as is into this like format, like open loop like this, no problem. You can use it this way, and this works. But if you are planning to put things in feedback loop, you're making the dynamics much more complex. And then we will see that these kind of complex dynamics will significantly affect the stability of the loop and things of that sort. So as an open loop amplifier, yes, the price you're paying is the delay, possibly more power. But primarily delay. Yes?
It's not just, I mean, open loop at lower frequencies, right? Because if you're open loop at a higher frequency with parasitics, you can still get an unintentional feedback from some parasitic.
Right. This assumes that these amplifiers are, they are not coupled to each other. The assumption here is that these amplifiers are not strongly coupled to each other. And there are scenarios, that's a good question. So you can say if they are strongly coupled to each other, there can be some internal instability because there's some internal capacity that creates some feedback loop and all those things. And that's absolutely correct. That would exhibit itself in terms of time constants and the transfer function overall, if you look at that. So you will see it, and it can happen. But nonetheless, if you could break them separate into 2 parts, I mean, you can clearly gain an advantage. And obviously, as you can probably guess from this example, it's not limited here, right? It should not be, I mean, 2 is not, there's nothing magical about number 2, right? Going from 1 to 2. So if you go to 3, we may get more, right? Now the question is, what is the optimum? Or is there an optimum? Or if you get to a point where you have infinite stages of gain 1, you would be okay, or almost 1. Because as a side note, right? So this is one of my favorite things. So if you have infinite stages with gain 1, almost 1, you're looking at this. So this is an infinitesimal over, and you have infinity of these, which basically is 1 over x. And if you take the x going to 0, what is this number? This is e. very crudely and roughly and mathematically inaccurately speaking, E is 1 to the power of infinity. A certain kind of one. It's not complete nonsense what I just said. It's partial nonsense, in the sense that if you have a 1 that's raised to the power of infinity and that's scaled at the same rate, that your infinity is scaled at the same rate, then you get E. But anyway, so we'll see. E pops up at some point. But, OK, so let's see what we can do. So now let's say in general, if you had a single stage, let's say you have a single stage, and its transfer function was, so you want to kind of like, and you want to break the gain. So let's say you want to have a total, a gain of total, and you want to break it into n equal stages, right? So what is the gain of each stage? So obviously, a1 of the stages, it has to be a1 to the power of n has to be a total, right? Because they get just multiplied by each other. Now, what is the transfer function? Let's say each one of them has a first order transfer function. Let's make a very simple assumption, right? So for each stage, h1 of s, you have the transfer function is a1 over 1 plus s of omega 1 per each stage, right? Now, we want to see what this is in terms of, so we want to solve for what is the bandwidth of this new system. So the transfer function of the total system, of the aggregate system, is going to be the transfer function of one of these to the power of n, right? It's multiplied n times by itself, which would become a1 to the power of n divided by 1 plus s over omega 1 to the power of n. Now, what we are really interested in is the 3 dB bandwidth, right? Which is the frequency at which the magnitude of this, as s being j omega, drops to 1 over square root of 2, or the denominator becomes square root of 2. So what we are looking at is the magnitude of h total of j omega h. So you can do magnitude square at the frequency at which this is 1/2, or more accurately, a total over half. So we want this drops by a factor of 1/2. So you're trying to solve for that. So what is that thing? It's basic. So this is a total. So this is this would be a total squared over half, sorry. So this would be a total squared here, because this would be squared. And this is magnitude squared. So this becomes like omega over omega 1, omega h over omega 1 squared to the power of n. Right? That's what that magnitude square thing is. Now, of course, these guys cancel. So this has to be 2. Right? So basically, what we are saying is that we are solving for this denominator being 2, which basically is another way of saying omega h over omega 1 squared is going to be 2 to the power of 1 over n minus 1. I take the nth root of both sides and subtract the 1. And then this is it. So then omega h over omega 1 is going to be square root of that. Or you can also write it as, just write it in terms of omega h. So you can say omega h is omega 1 square root of 2 to the power of 1 over n minus 1. But omega 1 is not really a constant. What is a constant in this kind of like for the assumptions we've made? For each stage is the product of the omega 1 and its gain. It's the gain bandwidth product, right? Because as you reduce the gain, omega 1 is going up. So we have to express that in terms of that unity gain. So we can say a1 times omega 1 is omega u, the unity gain, like that, up there. Agreed? But a1 is also not a constant. What we are looking for, we are shooting for a total. So I express a1 in terms of So I can write omega 1 as omega u over a1, but then I can write it as omega u over nth root of a total. Because this is a constant and this is a design target, right, in our model. Do you agree? This is the unity gain frequency and this is the target, I mean, again, in our simplified model. So I will plug that into here, and what I get is that I express it in terms of omega u. So I get a total to the power of 1 over n, 2 to the power of 1 over n minus 1. So in other words, let me just write the end result a little bit more clearly. The enhancement, so this is the enhancement of the bandwidth, or say bandwidth enhancement, which is basically the ratio of omega 1 over omega u, is going to be what is left here, which is basically square root of 2 to the power of 1 over n minus 1 divided by a total to the power of 1 over n. So for a given gain, this is the enhancement you get for a given number of stages. So if you plug in a number of stages, you can see what it is. So for example, let me give you an example. So for a gain of 100, I'm going to make a little mini table. So a total of 100. Let's say your target gain is 100, right? Like that example. If you have 3 stages, if you have 2 stages, of course, the enhancement, we saw that, what the enhancement was, right? It was 6.4. With 3, you get 11. I have a bunch of numbers. 5 is 15.4. 7 is 16.7. 9, or let's say like 8. 8 is 16.9. 9 is 16.96. And 10 is 16.9. And then if you go above that, then it starts dropping. So there clearly is an optimum, actually. And there are these curves that you can look at that show the optimum. So it kind of goes up like that and comes back versus n. So this is the enhancement. You can just plug in numbers and all this. And anyways, what is the reaction from more mathematically minded, slightly more mathematically minded, is that instead of plugging numbers into this thing and finding out what it looks like, do what? Take the derivative and set it to 0. It's actually a messy calculation. You can do it as an exercise. See, that's what the professors do, all the messy calculations. I won't do it as an exercise. I mean, you can do it if you want. But the end result is this. I did it. The end result is the following. The end result is that n optimum, the optimum number of stages for a given gain, is natural log of a total divided by natural log of e minus 1, which you can also write, if you calculate these numbers, 1.85 roughly natural log of a total. So this is what you will get in terms of what's the optimal. I mean, there's nothing magical about this because there's a bunch of assumptions made. So this number may not be the exact number you need. I'm just giving you an example. And I'm just telling you that there's an e in there and logs and things of that sort because of the way that like 1 plus x to the power of 1x works, right? This is with certain assumptions that may not exactly hold in reality. And the optimum gain, actually, the gain at that optimum is even more interesting. The stage gain, A1 optimum. So this is the optimum gain per stage. What do you think it is at that point? What is that optimum gain per stage when you hit that optimum number? You have the optimum number of stages. And this is independent of the A opt and all those things. It depends on what kind of like target gain. If you shoot for a gain of 10,000 or shoot for a gain of 10, the optimum gain per stage is the same. You're close. You said E. It's related to E. It's E minus 1. At that optimum. Now, if you, of course, do this thing, this may not be an integer, right? Obviously, because you're fitting a continuous function. So you have to pick an integer, obviously, the closest integer to it. And then the exact optimum gain would not be exactly E minus 1, because you haven't picked exactly that real number. You've picked an integer close to it. But this is actually very interesting. That this is independent of the total gain you're trying to get when you run this optimization. The optimum gain per stage to get the maximum bandwidth is E minus 1. And that's, you could think about it partly because E is one rendition of 1 to the power of infinity, or less mathematically cringeworthy statement of the 1 plus x to the power of 1x, and x going to 0 being E. You could also say defined as E. Because it's the product of things that are incrementally large, product of a large number of things that are incrementally larger than 1. So you can see that if you're designing wideband amplifier, broadband amplifiers, one of the things you can do is that you can break your gain into large number of stages as opposed to trying to get it all in one place. And you can see that the optimum gain per stage is pretty low, like 1.67, something like that. Right? It's not a lot. And it comes from this optimization. Any questions?